So far, what did we do about the determinant? We said that we have first inspired ourselves from the 2 by 2. The 2 by 2 determinant came from concrete calculations of how to solve linear systems with 2 unknowns and 2 equations. Anyway, then we gave a formula for any size of any matrix by using the cofactor expansion along a row or a column. And finally, we found that a practical way to compute the determinant is to combine this cofactor expansion with some basic elementary operations, okay? Either row elementary operations or column elementary operations, because both of the matrices A and A transpose, they have the same determinant, okay? So here, remember, it's very important, the linearity of the determinant. Okay, meaning what? That the determinant of what happened if, so the beauty here is with respect to one column on one row, it doesn't matter. So here is linear with respect to one column, so it is linear with respect to each column. So this is what's known as bilinear for 2 by 2, n linear if you have n by n. And what it means is that if you have a constant time a column, the constant comes out. If you have the sum of 2 columns, then you can have determinant of, for example here, so for example, determinant of, let's say we have A1, A2, and when we get to AI plus K times B, and then we go all the way to AN. This is the matrix with all these columns. So what we said is this is equal to the determinant of A1, AI, AN, okay, plus, and you can take K out, the determinant of A1 plus, I'm sorry, not plus, this is a column, this is a matrix column, matrix we're talking about. And when you get to AI, it's going to be a B and then AN, the last column. So this is what's known as the linearity or bilinearity or n-linearity of the determinant. It's really beautiful. This is, as we said before, this is false, okay? To get that the determinant of a matrix A plus a matrix C is equal to the determinant of A plus the determinant of C. This is false. Very easy to see it on a 2 by 2 matrix, huh? Okay. Now, what's amazing is this is the most amazing formula. It's really amazing. Okay, we have seen it before, but it is amazing. Most amazing formula is that the determinant of A times C, a matrix C, is the determinant of A times the determinant of C. One way to see this is through elementary matrices, but here I will just not focus too much on the proof, and we have that this. So also what we saw before, in fact, and we'll see it again here, is that if A has an inverse, okay, A inverse, then what do we know? We know that A times A inverse will give us IN, and therefore the determinant of A times the determinant of A inverse equal determinant of IN, which is 1. Okay, determinant of IN it's a diagonal matrix or upper triangular, lower triangular matrix, and you multiply the elements of the diagonal, you get 1. So here we get that the determinant of A inverse, first, we see from here that determinant of A cannot be equal to 0 because we have something times something equal to 1. And more than that, we have this equal to determinant of A. So the determinant of A inverse is 1 over the determinant of A. Okay, so we will see, next we'll see it, it's really beautiful, that in fact we have if determinant of A is not equal to 0, then A is invertible. So for example, if you take a matrix A, let A equal 1, 1, 2, and 2, 0, 4, 3, 1, 6, okay, is A invertible. One way to do this, okay, if we have a machine to compute the determinant, then it's very quick, okay? So here, let us take the determinant of A. So what do we have? 1, 1, 2, 2, 0, 4, 3, 1, 6, okay? And let's take 1, 2, 3. Let's take row 2 minus row 1, 0, minus 2, 1 minus 3, minus 2. And let's take the last one minus 2, the first one. So we get 2 minus 2, 0, 4 minus 4, 0, and 6 minus 6, 0. As we can see, the last row is all entries are 0, therefore the determinant is 0, therefore A is not invertible. Of course, if someone sees here right away, so if you see right here, if we see right here that row 3 is just to row 1, so 2 rows are proportional, the determinant is equal to 0, then yeah, you can see it quickly. If you don't see it, then you can do the elementary operations on columns or rows to find out that your matrix in fact is not invertible. In fact, is not invertible. So next, what I want to do is find what we are gonna see, something very interesting. Okay, so here let us look at so we can have so next what we want to do is so next what I want to do is to be able to work with or to find an example of applications of the determinant to find the inverse. This is really interesting. So here determinant, so how to find A inverse. So here A inverse by determinant. So this is one of the applications. Okay, so here so what do we have? We have A, which is given by Aij, And what we do, we come up with a matrix Cij, okay, which is minus 1 to the power I plus j times mij. So remember, mij is the determinant of the matrix from A that we removed row I with j column. Okay? So just for the sake of, let us take A, which is 3 by 3. Huh? So here, 3 by 3. Huh? 3 by 3. So Cij will be C11, C12, C13, C21, C22, C23, C31, C32, C33. Okay, so what is the determinant of A? And this is, of course, A11, etc., A33. Okay, so here, what is the determinant along any row? So it's going to be A11, C11 plus A12, C12, A13, C13. Okay. And if we go along any column, then we have a different formula. Okay. Anyway, so now what happened? How do I generate this product from the matrix Cij? Okay, if I multiply A with the Cij, I will not generate this one. But if I take Cij transpose, then what do I get? I get C11, C12, C13, C21, C22, C32. No, sorry. Two, three, and C31, C32, C33. Okay, so now what happened when I multiply A, which is A11, A12, A13, A21, A22, A23, A31, A33, A32, 33. Okay, time this matrix. So what do I get? I will get on the first one, so we take the first column of the Cij's, the transpose, of course, time the first row. So I will get A11, C11, A12, C12, A13, C13, etc. Okay? So you see, the first number will be the determinant. Okay? So what do we have now? A time Cij transpose. Okay? What we are going to find is determinant of A along the first row. And this determinant of A along the second row and determinant of A along the third row. What happened to the other ones? It's easy to see that for the other ones, it's another determinant of a certain matrix where two columns are the same. And if that's the case, then you will find 0, 0, 0, 0, 0. Okay? So this is really amazing. Why? In fact, there is a formula that is always true. So what's this? So this is determinant of A times I3. But in fact, this formula is valid for any size. So meaning, if A is n by n, okay, square matrix n by n, from this matrix, we come up with Cij. So remember, this is minus 1 to the power I plus j time Mij, the minors. Okay, and this Mij is just the determinant of A, where we remove the row I and the column J. Okay, and this matrix has a name. We call it the cofactor matrix. Cofactor, because all theCij's are the cofactors. Cofactor matrix of A. Okay, and what happened is when you take A time Cij, the cofactor matrix transpose, you end up having the determinant of A time the unit matrix In. It's an amazing formula. It's truly an amazing formula. Okay? So here, so what happened? We have two cases. Case one, okay, the determinant of A is 0. If that's the case, then what we have is that A time Cij transpose is going to be the 0 matrix, and therefore A is a divisor of 0. A cannot be invertible. Good. So A is not invertible. Case 2, so determinant of A not equal to 0. It's a number that's not equal to 0. In this case, A time 1 over determinant of A time Cij transpose is going to give me what? The 1 over determinant goes out, time equal to the determinant of A time In is going to be In. It's very easy to see that, in fact, the product here is commutative, and therefore A is invertible. And A inverse is, we have a formula, 1 over determinant of A time Cij transpose. Okay? Okay, so as we said, the Cij is the cofactor matrix. The transpose, Cij transpose, is known in the literature as the adjoint of the matrix A. Okay, and therefore, just fancy names. I mean, I'll be honest with you, I will live with the formula. It's not really complicated. It's 1 over determinant of A time the adjoint matrix of A. That's what it means. So it's nicer if you want that. Okay, so let us do an application of this. So here, example. So A is equal to 3, 1, 2, 2, 6, minus 4, minus 1, 3, and 0. So let's go to what are the cofactor matrix? Cofactor matrix. Cofactor matrix. So here, what do we have? Cij equal C11, C12, C13, C21, C22, C23, C31, C32, C33. So remember that you do have that plus minus, okay? So C11 is going to be, I'm not going to do all of them, but the point is going to be plus, because minus 1 to the power of 1 plus 1, and that's M11, which is plus 1, time, we remove the first row and the first column, 6, minus 4, 3, and 0, and that's minus 12. I'm sorry, not minus. Minus, sorry, 0. Sorry. So it's 0 minus 12, and that's plus 12. Okay, so let me just do one more. C to 1. So it's going to be minus 1 to the power 2 plus 1, M to 1, equal -1, because to the power -3, I'm sorry, 3 is -1, and we remove the second row. We remove the second row and the first column, so it's 2, -1, -4, and 0. And this gives me 2 times 0, 0. -4 times -1, +4, so it's going to be -4 minus -4 +4. Okay, so let me put the other ones. So the other ones are C12, 6, C13, -16, C22 equals 2, C23 equals 16, C31 equals 12, C32 equals -10, and C33 equal 16. So this gives me what? That the cofactor matrix is equal 12, 4, 12, and 6, 2, -10, -16, 16, 16. Okay, so now if you take the matrix A times the Cij transpose, okay, which is the matrix A, which is 3, 1, 2, 2, 6, -4, -1, 3, 0, time the transposer, so it's going to be 12, 4, 12, 6, 2, 16, -16, 16, 16. Oh, I'm sorry. -10. Okay, so if we do this, we will find that this is equal to, so the first one will give me what? So the first one, we know we're going to have the same element on the diagonal, so I leave it to you to check it. You will find that is 36. So what number is that? 3 times 12, 36, plus 12, plus 16. Yeah? So that would be what? 48, 58, 64. 0, 0, 0, 64, 0, 0, 0, 64. And in fact, I can also compute the second one if you want. So we take the first column of the adjoint matrix time, let's say, for example, the second row. So it gives me what? 12 plus 36 minus 3 times 16, 48. And obviously, that's 0. So anyway, so this is equal to 64 times I3. So what do we know? We know that A, the determinant is equal to 64, not equal to 0, and therefore A inverse does exist. And what do we have? We have A inverse equal 1 over 64, okay, time the cofactor matrix, 12, 6, transpose, because the adjoint, sorry, 4, 2, 16, 12, minus 10, 16. So here is a way of how to compute the inverse of a matrix. Let's do a beautiful example here. Yeah, example. Okay, set A to be equal C1, 0, 1, C1, 0, 1, C, where C is a number, where C is a number. Okay, so here, for what number C A inverse exists? For what number C A inverse exists? In other words, that A is invertible. Number one, if A inverse exists, okay, find it. Let us find it. Okay, so to answer this problem, okay, of course, if the question is for what number C A inverse exists, we compute the determinant and we have the answer. Not equal to 0, the matrix is invertible. But what if they ask us to find the inverse? If they ask us to find the inverse, the best approach to both of them is to find the adjoint. Okay, so here, first, find the adjoint of A. So let us do that first. Okay, so what is it? So we need to find all the cofactors. So we have C11 equal plus, because it's going to be minus 1. And we remove the first row, the first column, C1, 1C, and that will be C squared minus 1. So next, we go for C12, and that's going to be minus 1 to the power 3, minus 1, time 101C, okay, and that's going to be minus C. C13, so it's going to be minus 1 to the power 4 plus, and that's going to be 10, C1, it's going to be 1 minus 0, 1. C21 is going to be minus 1 to the power 3, minus 1, times 110C, and that's minus C. C22 equal plus, because it's going to be minus 1 to the power 4, plus, okay, C00C, C squared. C23 minus 1 to the power 5, minus, and it's going to be the determinant C011, and that's minus C. C31 equal minus 1 to the power 3 plus 1, 4, plus, time 1C01, and that's 1. C32 minus 1 to the power 5, minus 1, time C101 equals minus C. And the last one is C33, again minus 1 to the power 6, plus, okay, C11C, and that will be C squared minus 1. So what is now the cofactor matrix? Cofactor matrix. Okay, it's going to be, cofactor matrix is going to be C squared minus 1 minus C 1 minus C, C squared minus C 1 minus C, C squared minus 1. And if you take now the transpose, which will give you the adjoint of A, we will find C squared minus 1 minus C1 minus C, C squared minus C, and 1 minus C, C squared minus 1. Okay, we'll make a remark next where some stuff are not, well, I'll make it about symmetric matrices. So let's move on. Now we take A times the adjoint of A, and we will find C squared minus 2C 0, 0, 0 C squared minus 2C 0, 0, 0, c squared minus 2c. Okay, so what do we have? We have this is equal to c squared minus 2c times I3. So what do we have? We have a determinant of a is c squared minus 2c, and therefore, okay, a inverse exists if and only if c squared minus 2c not equal to 0. Okay, and we have a inverse equal 1 over the determinant time the cofactor or the adjoint, c squared minus 1 minus c 1 minus c squared minus c 1 minus c squared minus 1, sorry, minus 1. So here I want, just before I close this, make a remark. If A is symmetric, then and has an inverse, okay, then A inverse is symmetric. A inverse is symmetric, which will give us, in fact, therefore, the adjoint of A is symmetric, which gives us, which will give us that the cofactor matrix is symmetric. In fact, this is just simple to see it, but in fact, this is true even if A is not invertible. So what does it mean? It means that when you go to the cofactor matrix, the Cij. So you don't need to compute all of them. We could have avoided some time. In other words, what we need is compute these ones, and fill the matrix by symmetry. See, that's why. So it's interesting to know you don't have to compute all the 9. For example, for a 3 by 3, there were 9 minors or 9 cofactors. You don't need to compute all of them. Diagonal, yes. The one under diagonal or the one above diagonal, and you complete the matrix by symmetry.